Hello, everyone. Thank you all for joining. Welcome to Enrhythm Lightning Talks. I'm your host, Parag Katkar. I'm the head of consulting practices at Enrhythm. We have several awesome lightning talks lined up for you in the upcoming weeks. Our lightning talks are hosted every Thursday at 5:15 p.m. Eastern Time. And each week, one of our practice area consultants shares their knowledge on the evolving technology trends in the industry that will help you keep learning and growing in your career. And this week, William Kingsley, who is a senior Android engineer with us, is going to discuss Bluetooth low energy, which is also called BLE, and how it's used by Android. Devices using BLE are becoming increasingly common as a result of significant computing cost savings of the BLE technology. And many modern devices, such as Fitbit, blood pressure monitors, and industrial monitoring sensors, all use BLE for communication. So I'm super excited to learn more about BLE. So without further ado, let's get it started, William.
Thank you, Parag. Welcome, everyone. This is my second ever lightning talk for Enrhythm, and I'm super excited to be giving it today. As Parag said, today we'll be discussing Bluetooth low energy technology and specifically how it impacts the Android platform and how you can implement Bluetooth low energy technology into your Android application for the purpose of communicating with Bluetooth low energy devices. So to begin with, we need to ask the question, what is Bluetooth low energy? To answer the question of what is Bluetooth low energy, I choose to compare and contrast against Bluetooth classic technology and Bluetooth low energy technology. So what is Bluetooth? Well, Bluetooth was first introduced to mobile computing devices and phones back in the early 2000s, about 2000 or so. Bluetooth is a high-frequency hopping radio technology that transmits data packets within the 2.4 gigahertz band. Packets are exchanged through 79 designated Bluetooth channels. Each Bluetooth channel is about 1 megahertz in bandwidth, and connections can last anywhere from a few seconds with Bluetooth Classic to a few hours in length. Comparing that against Bluetooth low energy technology, we could see that BLE was first introduced back in 2011 and was introduced with Bluetooth 4.0. Bluetooth low energy, as its name suggests, consumes significantly less energy or power in order to facilitate device wireless communications than classic Bluetooth wireless technology. Bluetooth low energy also operates like its counterpart, Bluetooth Classic, at the 2.0 gigahertz band. It remains in sleep mode unless a connection is initiated. This allows Bluetooth low energy technology to provide cost savings to the battery life of your devices. And rather than using 79 designated channels, Bluetooth low energy uses 40 2 megahertz channels for data transmission purposes. Data rates are significantly higher than Bluetooth Classic on Bluetooth low energy, providing up to 1 megabyte per second of transfer times. It's also the preferred communication mechanism for communicating with many IoT devices nowadays. So think of like a wearable device or a Bluetooth beacon. This is more than likely using Bluetooth low energy in order to save on battery power consumption. Connections with Bluetooth low energy technology last for only typically a few milliseconds, and thus saving on battery consumption. The key differences that you really want to take away from this is that power consumption is significantly less with Bluetooth low energy. The range is a little less than that of Bluetooth Classic, but not by too much. The throughput is greater, connection speeds are a little greater, the number of connections is a little different, and it provides significant cost savings to the battery life of your devices. So how does this really work in practice with mobile devices or wearable devices that we find all over the place nowadays? Well, BLE devices are discovered by broadcasting advertising packets over 3 separate frequencies. These packets are discovered by those devices engaging in scanning processes. These scanning processes allow for the advertised packets to be discovered and thus for devices to initiate communications. Once advertising packets are discovered and the pairing process between devices is completed, devices are now considered to be connected and it can exchange data as needed. So what are some BLE devices out there in the world currently? Well, there's everything from wireless headsets, blood pressure monitors, wireless mouses, earphones. In my case, I actually have a pair of Galaxy Buds. They're really nice and they use Bluetooth Low Energy technology. Fitbit devices, portable speakers, industrial monitors, pacemakers, Wear OS devices on the Android side. Various Apple devices now use Bluetooth Low Energy, Bluetooth beacons, and many, many other IoT devices all out there in the world right now are all, for the most part, using Bluetooth Low Energy technology to facilitate communication with devices. So how is Bluetooth Low Energy used on Android, and what does that look like? Well, before we can answer that question, we have to establish some terminology. And this is reoccurring terminology that you'll see throughout really any practical implementation of Bluetooth technology. So what you may find is that this terminology will carry over to an implementation of Bluetooth technology on Apple devices, just the same as it would be on Android devices. So our first term that we define here is Android BLE. What is Android BLE? Well, Android BLE is just a built-in platform support to discover devices, request and transmit information from Bluetooth devices. This is more or less just APIs and interfaces that are provided to you by your Android OS that allow the device to utilize what is typically an onboard Bluetooth chip or a communication median that's just built right into the boards of the device. The next really important term here is the GAT, or the Generic Attribute Profile. This defines how data is exchanged using predefined attributes between devices. The next key term here is the peripheral. The peripheral is the device broadcasting the data. This is also referred to as the GAT server. The data is structured. The data the GAT server distributes and can distribute is structured as definitions. And through these definitions, devices can query the GAT server for services or different characteristics, which are nothing more than various atomic pieces of data that are available on the peripherals database. The central is the device that scans requests and uses data given by the peripheral. Also, this is also referred to as the GAT client. So the central is the client device and the peripheral is the server device. If you were, as an example, to connect a smartphone device with a portable speaker device, the speaker device would actually be the GAT server because it's the device providing services that the mobile device is requesting to use. Thus, the mobile device or the mobile smartphone device is the peripheral in this relationship. Services are a set of provided features and associated behaviors to interact with the peripheral. So each service contains a collection of characteristics. These services are nothing more than the services that the peripheral device offers to potential GAT clients or centrals. Characteristics. The definition of the data divided into declaration and value. You can think of characteristics as more or less a map type in a programming language or as a dictionary. These are key value pairs. A characteristic uses permission properties such as read, write, notify, and indicate to get data from the peripheral device's GAT server database. The descriptor is an optional attribute nested within a characteristic that describes the specific value and how it can be accessed. As an example, this might contain information such as the privacy setting or permissions setting of a particular characteristic. So this could provide some information on a characteristic, and it could explain something like this characteristic is read only, or write only, or notify only, as an example. UUIDs, or universally unique IDs, these are used to identify characteristics, services, and devices. They're used very commonly in Bluetooth and Bluetooth low energy technology. They're used in other situations to identify devices and identify specific services so that services can be differentiated between in the LE environment. So looking at what all this looks like on Android, today I don't have a demo application for you because, quite frankly, creating a BLE application is quite hard, and I'll explain why that is in just a moment. So here, instead, I have some snippets and screenshots of what the code would look like in order to use BLE technology on an Android application. The very first step to any BLE communication is first finding devices that that you may be able to pair with or connect with. This is accomplished by first getting a handle or reference to the device's BLE adapter. With the adapter in hand, we can then define a function, in this case, the scan LE device function. And we use our adapter, and specifically the BLE scanner that our adapter can provide us with, to scan for devices that are within range of the device. Once we've done this, we can define a scan callback function. And what this callback function does is it observes or changes in data that results from our scanning process or from the discovery process. Once we have that data in hand, as implemented by our scan result callback function, we can then choose to use that data to populate something like a list, for example. So we can list out all the various devices that are available within our local area. The next step in any communication process is to connect to the GAP server that may be advertised by a device that's within our area and that is willing to accept connections. We do this by, once again, using our BLE adapter to acquire a device object using the MAC address of the device that was previously discovered in our scanning process. Once we have the device object, most notably, this is a BLE device object, we can then use the built-in connect GAT function, passing in a callback to this function that will help us handle the state of our connection to this device. Once our connection has been established, we'll then be told of any changes of the state by our Bluetooth GAT callback function. So for example, if there's a successful connection, and we can see this in step 3 here in the slide, if there's a successful connection, our Bluetooth GAT callback will inform us of that by exposing and overriding the on-connection state change function. If there's any type of state disconnect, such as we get out of range of the device that we're attempting to facilitate communication with, we'll be notified of that failure of communication or of disconnection with the device through the Bluetooth GAT callback function. Now, here's the tricky part. Transferring BLE data is most definitely the most difficult part of this entire process. So to begin with, you need to override a few additional functions that the Bluetooth GAT callback object can provide us with. Most notably, we need to override the services discovered function. This will allow us to implement logic to communicate with the GAT server. The next step here is to implement a broadcast receiver. And this broadcast receiver is really doing nothing more than broadcasting application-wide updates concerning our Bluetooth disconnection state. So this could be anything from informing us that a disconnection has occurred, or that services have been discovered on this particular peripheral device. Could be anything like that. To continue, say we now wanted to read some information from our peripheral that we have successfully connected to. What we then need to do is override the uncharacteristic read function that's provided to us by the Bluetooth GAT callback object. This allows us to observe for characteristic data changes within the peripheral device or GAT server. We can see this in the top left snippet, where we override the uncharacteristic read function, pass in the characteristic that we're attempting to read from, the status of it, if we're concerned with that, and also the particular GAT object that we're trying to read this data from. We then check whether or not the status of this particular GAT object is successful. And if it is, we broadcast an update to some other part of the application that's listening for changes. If we find that we are indeed successful and the status of the Bluetooth GAT object is of type success, we can then proceed with attempting to read data from the peripheral device. What this looks like can be seen over in the right-hand pane. Here we have the definition of the broadcast update function. Here we can see we have it defined as a parameter, the action, and also the characteristic that we're attempting to perform some read or write action of. In this case, we're performing a read action. So the example that you see in front of you here is actually an example of attempting to read data from a heart rate monitor. So once we've implemented a function that allows us to read the data from our peripheral device, and in order to read our data, this typically requires that we parse out what is a byte array that the peripheral device will provide us with. And with that, once we parse that byte array into a more meaningful format, we then have successfully read the data from the peripheral device as the central. So with that data in hand, we can now really do whatever we want with it. In this particular example, we're rebroadcasting using an overwritten send broadcast function here, the data that we read from our peripheral device, notably a heart rate readout. We can then do whatever we want with that data. We could have an activity or a fragment or another broadcast receiver even receive this data that we have read, and you can really do whatever you want with it at this point. Writing data looks very, very similar to the reading process, except it doesn't require that we parse our data, that we parse byte array data that we might be getting back from the central. Rather, we simply call a function that's provided by our peripheral object, and that would allow us to simply write data to whatever the peripheral device may be, whether it be a heart measurement or a fitness device. It really doesn't matter. There's two other types of permissions or actions that you can take with peripheral devices or devices acting as peripherals, and that is the notify characteristic and the observe characteristic. However, you wouldn't really use these particular actions or permissions unless you needed to observe data from, let's say, a fitness device. If we were interested in knowing the heart rate every second that the fitness device may be able to read out to our mobile device, as an example, you might want to use the notify characteristic action and utilize that action as opposed to just typically a read action. The reason for this is because notify would allow us to be notified of any changes to that particular characteristics data. And thus that would provide us with a continuous sequence of data over time as more and more data is generated and provided to us by that fitness device. So what is my experience with Android BLE? Well, I can tell you from my experience with Northrop, my former employer, and as my last project being with them, a BLE application, I can tell you it's not the most easy type of application to build. Building a BLE application, especially a robust one, is very, very difficult. And the reason for this is because of error-prone features within the Android built-in support and APIs. And I'll explain that just a little bit more in a second. So to expand upon that, custom BLE solutions are difficult to build well. Creating those necessary components is easy. Debugging the various platform built-in features and functionality is rather difficult. And this is due to multi-threading that occurs within the BLE built-in platform support. One of the features of the built-in Android BLE libraries and APIs is the ability to discover devices. However, this process is rather error-prone. It can be a little difficult to get quite the right data that you want to be reading from devices within your surrounding area. This can be due to anything from the range being a little spotty on a device. So as an example, if you were to hold your mobile device and scan for BLE devices, you may find that a device may blink in and out of your range, and that can cause some weird things to occur when you're trying to read data from that device. You can encounter situations where some pieces of data are simply missing because they weren't properly transmitted. The second big hurdle to building a BLE application on Android currently is the fact that the Google documentation is rather basic and is in desperate need of improvement. It seems that this particular set of documentation Google hasn't yet got around to updating and bringing into alignment with the other features that Android has to provide as a platform. Most of the examples in the documentation tend to be rather contrived and very, very basic. And so while they're great to get you up and running, in order to build a robust application, well, it's a little difficult because they don't give you much more than just the basics to start with. Building a service in order to manage your BLE state is typically a good idea on Android. This could be anything from a long-lived service to a bound service. And this is actually a best practice that Google recommends when working with BLE. This is because you could have certain actions within an Android application occur in the background, and those actions in some way be associated with your BLE functionality within your application. A service in this instance allows us to communicate with our BLE device, the peripheral device, or the server device, whichever terminology you prefer, seamlessly without interrupting the UI, as an example, or seizing up the main thread. A service is a good place where you can do a lot of multi-threading and allow us to really manage the state of that BLE connection or establish connections with BLE devices without disrupting too many other features of your Android application. The Jetpack libraries work considerably well with Android BLE built-in support, given the age of the BLE built-in support. I found that building a Compose application utilizing Android BLE was quite painless for the most part. There's a few strange things you might have to overcome, such as the way in which data is processed, acquired, and observed in the BLE built-in support framework. Doesn't always work all that well with the paradigms that Jetpack Compose, for example, seeks to promote in modern Android applications. But it is very integratable with the current iteration of Jetpack Compose and the Android BLE built-in libraries and APIs. So in conclusion, Bluetooth is a wireless radio technology operating at the 2.4 gigahertz band. The number of devices using BLE is increasing, and it's increasing daily. Most modern mobile devices will support some type or some standard of BLE communication. BLE communication uses significantly less energy, and thus is why BLE is very broadly being adopted for embedded or wearable devices, ubiquitous computing devices, and really IoT devices everywhere. You could actually perform thousands upon thousands of BLE, individual BLE communication sessions without ever greatly decreasing the capacity of your battery, which is very impressive. You would have to be issuing hundreds, if not thousands, of BLE data transfers within a single second to ever really have a significant impact on your battery life, which is really impressive. The BLE APIs and interfaces typically require, on Android, lower level programming. And this can be a little bit of a headache for developers who don't really want to do that lower level programming. But I would say all in all, it's not too bad. The GATT server does not send data on its own, and this is an interesting distinction compared to other wireless communication technologies or Wi-Fi connections. Rather, it only sends data when client devices request it to do so, with the exception of the notify action or permission if you have it set, in which case a connected client device will be notified of any changes that occur on the server side. Google's documentation is very basic, desperately needs improvement. It could be improved by Google adding an additional BLE code lab, something like that, just to spruce up the documentation a bit. Bluetooth technology is improving and improving rapidly. As we've seen from the presentation here, BLE technology has actually only been on the market since 2011 and is undergoing significant improvements really on a daily basis. There's a very active and prominent community of BLE developers that are working very, very hard to improve the technology. So as the technology improves, we can only imagine what new possibilities there may be as the throughput, the connection range, improved battery usage, all of these things improve as the technology matures over time. Here I have some useful links that I used to construct this presentation, most notably the Android documentation for Bluetooth technology, how you find Bluetooth devices, connect and transfer data on Android. I've also included here the Bluetooth website URL and a few Medium articles that do, I think, a really good job of breaking down how you perform and utilize a BLE technology on Android. So with that, I leave it up to the audience. Is there any questions?